Hi everyone. Addressing your feedback today about my lecture on equilibrium. Where did you get the value 0.0313 for this reaction, H2O liquid in equilibrium with H2O gas? And I said the equilibrium constant for this would be products over reactants, except so that's going to be partial pressure of the water in the vapor phase over the liquid, except we leave liquids and solids out of the law of mass action. And I said that this happens to have a value 0.0313 atmospheres. Where did you get that value? That happens to be the vapor pressure of water. That's water's vapor pressure at 1 atmosphere. And this equilibrium reaction describes the vapor pressure process. Vapor pressure is a process where a liquid achieves equilibrium with the gaseous phase of that liquid. You have a constant rate of evaporation and condensation. So you have evaporation, you have condensation, and when that happens, you set up a vapor pressure for the liquid. And the vapor pressure of water is 0.0313 atmospheres. So that's just something you would have to look up. I happen to have that value somewhat memorized just because, I don't know, I've learned it at one point and I figured it was good to have it on hand. When do we use the law of mass action? You will use the law of mass action so many times it's not even funny, but you will use it, well, certainly you'll actually end up using it when you're describing acid-base chemistry, because acids and bases themselves, we tend to think of, to a first order approximation, we tend to think of acids and bases as being types of compounds. Later, very soon, I will try to impress upon you it makes more sense to think of acids and bases as a class of reaction. You have an acid-base reaction. And those reactions also tend to reach equilibrium. And so you will have equilibrium constants for acids. We'll call them the acid dissociation constant or the base dissociation constant. And those expressions are just the law of mass action. Before we do that, my plan was to talk about solubility equilibrium. We'll have KSPs, or capital K subcase SP for solubility product. Point being, that is also an illustration of the law of mass action. I talked about today how Henry's law is an illustration of the law of mass action. So when will you use it? You will use it just more times than I can come up with than off the top of my head. But those are just a few examples. So you'll use it to describe a reaction. You'll use it to characterize a reaction, to say whether the reaction favors the products or the reactants. I take that back. You won't use the law of mass action to do that. You'll use the value of the equilibrium constant to do that. But yeah, many reactions you will want to conceptualize in terms of ratio of reactants to products, and that's given by the law of mass actions. Why do the oscillations equal out? You know, I'm honestly not 100% sure about why. To some extent, it's kind of like, oh, what's a good example? So imagine you have a spring, a ball that's weighted on a spring, and so the spring, you set it to oscillate. So the spring bounces up and down, up and down, up and down, until eventually it slows and then it hits the same spot. According to physics, that oscillation actually should go on forever, in the absence of any other interaction. The fact that the spring doesn't interact with anything else. You should have conservation of energy. But it does interact with other things. Where the spring is attached interacts with the base. The ball experiences friction by interacting with the air. And so similarly in that reaction that I showed you, there's essentially to some extent there are losses. There are additional losses other than just that forward reaction and backwards reaction. Some energy is lost as heat, and so that kind of acts like friction, for lack of a better word, for the reaction. There are other side reactions that are occurring that use up some of the reactants. So eventually all those other side reactions and whatnot cancel each other out. They kind of serve as damping on the reaction. So I admit that's a bit of a hand-wavy explanation. But I'm glad that you're interested. So I will tell you, maybe if you're interested, come and see me during office hours and we'll tease it out together. So this is a forward-looking question for, which is, when will Q be introduced? I was not planning on talking about Q, which is the reaction quotient, until next week. Reaction quotient, this will frustrate people, or it will frustrate some people, because I remember it frustrating me, is I will also define the reaction quotient as being described as concentration of products over reactants raised to their molar coefficients. So mathematically, it has the exact same form as the law of mass action, but essentially the reaction quotient is a way of quantifying whether a system is at or not at equilibrium. So I mentioned this in passing in my lecture today, but I'll say it again. The law of mass action says that at equilibrium, the concentration of the products over the concentration of the reactants is always equal to a particular value when you're at equilibrium. Your system doesn't need to be at equilibrium. And a way of quantifying just how far away from equilibrium it is, okay, maybe I have too many products. How much is too many products? You can quantify that with a reaction quotient. So they have the same mathematical form, but they're referring to completely different concepts. We'll use reaction quotient as a way, again, of quantifying how close a system is or is not towards equilibrium. What's the difference between equilibrium and dynamic equilibrium? So that's a good question. Equilibrium is some steady state, being in a state of balance of opposing forces. So it's very much like a physics definition. So just general equilibrium. So I'll give you an example, like the same example I had before where I had a spring that was attached to a ball that was attached to a spring. If the ball is just hanging there and it's attached to the spring is not springing, the spring the ball experiences a weight of gravity, it experiences the force of gravity, but the spring also has a pull on the weight. And so as a result, you have a balance of a force that's pulling this way and a force that's pulling this way. Those forces can balance each other out, and then the system is at equilibrium. That's just general, what we call general equilibrium. Chemists usually don't talk about that type of equilibrium. We talk about dynamic equilibrium. Dynamic equilibrium is when you still have a balance of some sort and things are no longer changing, like with the spring. It's no longer bouncing up and down. It's staying in the same place. Chemists will also talk about a state where things are no longer changing in terms of concentrations, no longer changing. But we call it dynamic equilibrium in the sense that things are still changing, but microscopically speaking. Reactants are still reacting and products are also still reacting. The reaction continues, but the concentrations are stable. So that's what we call a dynamic equilibrium. The example I gave, I mentioned this in one of my classes and I forgot as an example offhand. So I'll mention it again for people who were in the other class. Imagine you have two countries where people are allowed to go back and forth across the border. You might have 100 people going from country A to B a day, and then 100 people a day going from country B to country A, back and forth. Their populations remain the same, but people are still going back and forth across the border. People are leaving one country, and people are leaving the other country, but they're leaving and arriving at the same rate. That's an example of a dynamic equilibrium in the sense that change is still occurring, but there is no net change. So dynamic in terms of change, equilibrium in the sense, dynamic in the sense that things are still moving and there's still things going on, but equilibrium, dynamic equilibrium in the sense that there's no net or bulk change anymore. How do spontaneous reactions correspond with equilibrium and reversible reactions? So I'll just kind of riff on this. For a reaction to attain equilibrium, it needs to be a reversible reaction, meaning that it can go backwards with no loss of energy. And many reactions are like that. Many processes are like that. Examples of a process that is not reversible is one like this. If I have a bottle of water where the cap is open, that is not going to be a reversible process in the sense that once the water leaves the bottle, the water vapor leaves the bottle, it will never spontaneously come back. We need to exert some force of our own to make the water go back. That would be a non-reversible or an irreversible process. So that system will never reach equilibrium. For a system to reach equilibrium, the process that's going on in that system needs to be reversible in some way. So what is a spontaneous process? A spontaneous process is one that will occur without any external driving force. So meaning that left to its own devices, the reaction happens without you or some other reaction forcing it to occur. That's what a spontaneous process is. How does that relate to an equilibrium process? I will just say in passing that a spontaneous process is one that strongly favors the forward reaction, if that's how you've written it. If a reaction strongly favors the forward reaction, meaning you have a very large positive equilibrium constant, that will be a spontaneous process. If you have a very small equilibrium constant, then we'll say that the reverse process ends up being the spontaneous process. That's all I will say about that. We'll talk more about spontaneity and equilibrium later when we talk about thermodynamics. I really don't want to spend too much time on that just now, but I don't want to leave you hanging. What are the units for the equilibrium constant? Formally speaking, the equilibrium constant has no units. The way it's frequently written, it will appear to have units, and that's because even the way your textbook writes it is not 100% correct. Technically, so let me give you an example. Yeah, I'll just do this. I'll do it like this. The equilibrium constant, if I had some reaction like this, and I will make this basic here, little a moles of big A in equilibrium with little b moles of big B. Technically, the formal equilibrium expression for this is concentration of B raised to the B divided by concentration of A raised to the little a, and then each of these concentrations is divided by some reference concentration. Frequently, and again, this may make a little bit more sense when we talk about thermodynamics. We talk about reference points. These are supposed to be reference concentrations, and that reference concentration is 1 molar. So we don't usually introduce them at this point. We don't talk about it at this point because it just adds on more complexity to the equation. And functionally speaking, it doesn't do anything different because I'm just dividing by 1. So the numbers don't change at all. What does change is the fact that I have some unit with respect to concentration here. I'm dividing by my reference concentration, and so those units go away, these units go away, and then formally the equilibrium expression has no units. So the point being that I kind of didn't, I admit I didn't discuss that in too much detail today, but it's a good question, and it's a noteworthy question that formally will say that the equilibrium constant has no units. When do you use the law of mass action, and when do you use Henry's law? All right, that's actually a good question because I talked about this today in one of my classes and not in the other one. So let me talk about that right now. I used Henry's law as an example of the law of mass action. Henry's law derives from the law of mass action. So when would you use Henry's law and not the law of mass action? You would use Henry's law when you're trying to describe an equilibrium process between a gas and an aqueous system. Let me describe that. If I had carbon dioxide gas in equilibrium with carbon dioxide dissolved in an aqueous solution, so this was when I was making the soda water, that sets up an equilibrium process. Henry's law says that the concentration of CO2 in the aqueous phase should be equal to some constant times the partial pressure of the CO2. That is Henry's law. The law of mass action for describing this equilibrium process says, okay, there is some equilibrium constant, and that equilibrium constant should be related to the concentration of the CO2 in the water divided by the partial pressure of the CO2 above that water. And then I did a little math trick, and I multiplied both sides by the partial pressure. I moved the partial pressure over here, and I got a constant times partial pressure of CO2 is equal to the concentration of CO2 in the water. And this shows how this is Henry's law. Mathematically, it has the same form as Henry's law. Some constant times the partial pressure is equal to the concentration of the CO2 at equilibrium in the water. That's essentially what's being described by Henry's law, that if you have some gas above a liquid, there is a preferential solubility of that substance in that liquid, and that's given by Henry's law. Again, point being, Henry's law is a special case of the law of mass action. You would only use it if you were trying to describe a gas in equilibrium with an aqueous, or it doesn't have to be an aqueous solution, but a gas in equilibrium with some solution. Will there be a lot of equilibrium questions on the test? Absolutely not. There will be no equilibrium questions on the test. Can you list the topics that will be covered on the test? Broadly speaking, most things from Chapter 12, not including, osmotic pressure and colloids. So it will have the concept of solubility, that it's this preferential amount of solution of solute dissolved in solution. The energetics of solution, that will be covered as well. The factors that affect solubility, like dissolves like, intermolecular forces, comparable intermolecular forces, that will be covered as well. What else? Colligative properties of solutions. So things like vapor pressure lowering, the vapor pressure of a solution being lower than the vapor pressure of the pure solvent. Colligative properties like boiling point elevation and freezing point depression. So that should take you up to, I think, sections 12.7, I want to say, 12.6. And for chapters 13, it's going to cover sections 13.1 to 13.4. So rates of reactions, the rate law, that is the differential rate law, orders of reaction, integrated rate laws, and maybe just the bare minimum of collision theory. No real calculations with collision theory. Because as I said, I took those off of the homework. I'm not going to hold people responsible for calculations regarding collision theory and the Arrhenius equation. But I would still expect people to know about a little basics about collision theory and activation energies and temperature dependence of rates. Will K equilibrium ever be or get close to zero? So it will never be at zero, because zero would imply that you have zero solubility, that none of it goes into solution or none of it goes to products. And if that's true, then the reaction doesn't happen at all, and it doesn't make sense to describe it as a reaction. The reaction just doesn't exist. So in that sense, I will say it will never be zero. It can be very, very close to zero, meaning it can be very, very small. So the way I express that is K can be very, very much less than 1, and I gave an example of one reaction where K was about 10 to the negative 31. So that's pretty darn small. There are smaller numbers. I mean, sure, there's an infinite number of smaller numbers, but K can be very, very close to 0, meaning it essentially doesn't happen, but it happens a little bit. Sometimes the reaction occurs, but to a very, very small degree. How do you determine orders of reactions? Still confusing. Okay, so I think that's in reference to how do you determine. Today I showed like these forward reaction and a reverse reaction, and I wrote the rate laws for them. In general, you can't just write the rate law for a reaction based on its balanced equation. There are prescribed methods for determining the order of a reaction, which is the method of initial rates. So I gave a worksheet on that. The quiz, the first question on the quiz was essentially applying method of initial rates. You change the concentration and you see how the rate changes. That's essentially what's given by a rate law. So you can do it that way, or you can do it graphically by looking at the integrated rate laws, looking at how the concentration varies with time. Those are the only two ways that you can determine orders of reactions. So if you're having trouble with that, I would say look into the textbook, look into the either the worksheet or some of the problems on the homework which deal with orders of reaction, deal with integrated rate laws, orders of reactions, graphical interpretations of integrated rate laws. Those are how you determine orders of reactions. Why are solids and liquids left out of the law of mass action? There's two explanations for this. There's the formally correct explanation, which I don't really want to go into too much detail because it's opening up a can of worms. And then there's the hand-wavy explanation, which is not 100% correct, but it's correct enough. And so I'll give you guys the hand-wavy explanation first, and then I'll give you the more correct version. The hand-wavy explanation is that, okay, yeah, you can write in, say, I'll do it for this process. I can write for this reaction. I could, if I wanted to, write in concentration of H2O as a gas over concentration of H2O as a liquid. We will frequently be interested in calculating equilibrium concentrations, calculating them in the sense that we expect them to be variable. They would change depending upon the conditions of the equilibrium system. But solids and liquids are incompressible. Their volumes don't change, and we define concentration as the amount of material per unit volume. Solids and liquids, it's hard to change their volumes appreciably. Solutions, you can definitely change their volume. Add more solvent, and then the solute's concentration drops. For gases, their volumes change. You either decrease the pressure or you change the pressure. You can decrease and change the pressure, or you can decrease and you can change the temperature. So those substances have variable concentrations. So in terms of calculating concentrations, we leave out the concentrations of solids and gases in the sense that we don't explicitly write them in the law of mass action because their concentrations are constant. They don't change. Because they are constant, their value normally just gets lumped in with the equilibrium constant. So I will sort of create, what we kind of conceptually do is we lump together the concentration of the liquid, so I'd multiply both sides by concentration of water, and then I'll just write in a new formal equilibrium constant, which is equal to the concentration of the liquid in the gaseous, the concentration of the water in the gaseous phase, where K equilibrium is equal to these two values. We can't really decompose them, or deconvolve them? Yeah, deconvolve them, and we don't really need to or care to, because we usually aren't concerned with calculating the concentration of liquid water. It's a constant. So we'll just write the equilibrium constant. So the short answer is that their concentrations don't change. That's the short hand-wavy answer. The formal answer is that, again, admittedly, this is going off on a little bit of not a tangent, but opening up a more detailed, more formal, like P-Chemy detail, is that really the equilibrium expression is written in terms of, not concentrations, in terms of activities, which is how relatively reactive a substance is compared to some reference point. So we've seen that, like, for instance, rate of reaction seems to depend on concentration. A concentrated mixture is more reactive, reacts more quickly and vigorously than a less concentrated reaction mixture. So we'll say that the activity, quote unquote, of the concentrated system is higher. Liquids and solids have finite or constant activities. Their activities are always going to be the same relative to their reference activity. So that approximate activity is 1. It is always the same. Again, it's kind of how we write it as a ratio of concentrations to some reference concentration. We're writing the activity of a substance as being how does it change relative to some reference activity. But solids and liquids, again, have constant concentrations. Their activities don't change, so their relative activities are always 1. So they don't get factored into the equilibrium expression in the sense that their value is always 1. So they just get left off. Can you finish the math for question 3? Yes, I can. So question 3 from today in lecture, the clicker question was this one. That if I have a reaction which is 2 hydrogen sulfide molecules reacting to give me 2 hydrogen molecules and an S2 molecule, and I will say that these are all gases, you actually do need to be careful about the states of matter now that we're talking about laws of mass action. And I said that in a 4-liter container, there's 1 mole of hydrogen sulfide, 4 moles of hydrogen gas, and 0.8 moles of disulfur. And then I asked, what is the value of the equilibrium constant? Well, according to the law of mass action, the equilibrium constant should have the form concentration of hydrogen gas squared times concentration of the disulfur over the concentration of the hydrogen sulfide squared. Concentration is defined as moles over volume. So I can't just plug in mole quantities here. I have to divide all of these quantities by the volume, or 4. So I get a concentration here of 4 moles per 4 liters squared times, that's 0.8 over 4, and then 1 mole over 4 squared. So let me see here. 4 over 4 is 1, so I have 1 squared times 0.8 over 1/4 is 1/4 squared is 1/16. So I have 1 over 1/16. I mean, you can just plug this all into a calculator, and at that point, what you'll get is 3.2. So the equilibrium constant there has the value 3.2. Can you title the topic being covered in lecture and not just number the boards? That's a good request. I apologize. I thought I did that, and then I realized I could have been more descriptive. So I started out by writing equilibrium on the far left board. I should have been more concrete and said this is going to be a discussion about equilibrium constants and the law of mass action. So I apologize. I'll try to be more concrete about that in the future. What is the difference between the law of mass action and the equilibrium constant? They're very, very closely related. The law of mass action says this ratio. This is the law of mass action for this reaction. In general, the law of mass action says the ratio of the concentrations of products over reactants at equilibrium is equal to a constant. So this entire equation, this entire expression is an example of the law of mass action. That if you have a reaction that's at equilibrium, the ratio of the products over the reactants is equal to a constant. That's the law of mass action. The constant that they're equal to is called the equilibrium constant. So equilibrium constant has some particular value. It is a value. The law, it's a number. It's a number that is different for every reaction, but at the end of the day, it's just a number. The law of mass action is an equation. So yeah, KEQ equilibrium constant is just a number. The law of mass action is a collection of quantities that are all related to each other in an equation. How do you determine if K equilibrium is much larger than 1 or much less than 1? Not easily at this point. You can do it instinctively. We say that a process that has an equilibrium constant much larger than 1 is a process that very much favors a forward reaction. So any reaction you can think of that happens to completion, burning something essentially goes to completion. Like cooking an egg, that's a process that goes to completion. Those are ones where you could describe that equilibrium actually, I would say that's not a good example. Cooking an egg is an irreversible process. Let me see if I can. I don't want this video to go on forever. Any process that heavily favors one direction, one direction for the reaction is one where the equilibrium constant is very, very large. So you can answer that instinctively if you have an instinct about whether a reaction is very favorable or not favorable. Your question is, how do you determine that? So you either need to have that instinct, or once we get through our section on thermodynamics, you can calculate equilibrium constants in terms of energetics. So you can look at the energy, the relative energies, and technically the relative free energies of products versus reactants, and then you can decide, okay, if the products are much more energetically favorable than the reactants, that implies that the reaction should favor the products. They're lower in energy. In that case, the equilibrium constant is much larger than 1. But that can be hard to predict without any other instinct. So I will say that at least at this point, for the near future, I won't be asking you guys to determine if K equilibrium is very large unless I've given you some other information, like saying that the forward reaction is favored. What's the difference between K and K equilibrium? I will have a tendency to write big K, uppercase K, referring to K equilibrium, and I will frequently just write an uppercase K and write them as the same. They're the same thing as far as I'm concerned. What's the difference between K and the rate constant? those are less related to, I mean, they're related to each other, but they are not the same thing. The rate constant is referring to 1/2 of an equilibrium process. In a forward reaction, the forward reaction has some lowercase forward rate constant that describes fundamentally how fast that forward reaction is. The backwards or reverse reaction has another lowercase k rate constant. And big K, the equilibrium constant, at equilibrium is equal to, let me make sure I get this right, K, lower k reverse over, is that right? No, I had that backwards. It should be K forward over K backwards, yeah. Uppercase K forward over lowercase K reverse. So again, these are the rate constants for the forward and reverse reactions. This is the equilibrium constant. For the equilibrium reaction, which again, the equilibrium reaction takes into account that there are two competing reactions, a forward and a reverse reaction. So what's the difference between them? I mean, you could look, there are lots of difference, but fundamentally that's it. One, the rate constants are normally thinking about a reaction in only one direction, and they describe the fundamental speed of that reaction in that direction. The equilibrium constant tells you the relative favorability of the forward versus the reverse reaction. If the forward reaction is just fundamentally faster, yeah, they're going to kind of win out, and the reaction is going to favor the forward reaction. And so you'll have a very, very large rate constant. You'll have a very, very large equilibrium constant, and you'll have a lot of products being made. Okay, and one last question here. Why does the concentration of hydrogen, this is referring to the first example I gave today, which was hydrogen reacting with I2 and making HI. Why does the concentration of HI increase the reverse reaction as time goes on? Shouldn't the concentration decrease because HI is becoming H2 and I2? It eventually does start going backwards, so, but initially, this is saying initially, before you reach equilibrium. So I'm going to be plotting out just the concentrations here. If I start with only H2 and I2, at first their reaction is very, very fast, so it has a very steep slope. And because their reaction is fast and it's occurring in excess, that's not the right way, but it's occurring very readily, they are producing HI. So why does the concentration of HI increase in the reverse reaction? It increases because initially that reverse reaction is very, very slow, and you don't lose much of it. Most of it is being produced only at that phase. So initially, yeah, you start losing hydrogen. So this is referring to hydrogen and iodine concentrations. This is referring to hydrogen iodide concentrations. Initially, you're just losing reactants and producing products. Sort of like if we weren't thinking about the reverse reaction at all yet. If we were just thinking about this the way we had last week before we started talking about reverse reactions. But then over time, when the reverse reaction starts to speed up, then its concentration starts to level out. It's not just an exponential decay where it goes on forever, and this one is also not an exponential decay where it goes on forever. Eventually, they both flatten out, and their concentration stops changing, and that's when it reaches equilibrium. So why does the concentration increase in the reverse reaction? Again, it increases at first as it's being produced by the forward reaction, and then the reverse reaction speeds up as the concentration of a hydrogen iodide starts to go up. And so as a result, that's why its rate of loss actually starts to level out. Or rate of production, I guess. Net rate of production starts to level out. Okay, those are all of your questions for today. I will be in my office all day tomorrow from around 9 to 5. So if you have questions, please feel free to stop by and ask them before the midterm tomorrow. Have a good evening, everyone.